A perfect equilibrium between the simple and the intricate is woven deep into the fabric of the universe. I invite you to join me on an exploration that merges science with a sense of wonder, tracing a path from the light that unveiled physics' deepest secrets to the enigmatic quantum processes that animate life itself. You will see how concepts developed to explain a glowing light bulb ultimately led us to grasp the bizarre behavior of subatomic particles, and how these same hidden principles govern everything from the flight of a bird to the photosynthesis in a leaf. To truly comprehend the physics of our universe is to do more than just study the cosmos. It's to uncover the invisible web that connects everything, ourselves included. Science, which can often appear to be a confusing maze of theories and equations, is fundamentally a journey to understand the world we inhabit. Have you ever felt a sense of being dwarfed by the sheer scale of the cosmos? Maybe you've looked up at the night sky and wondered why stars seem to flicker, or how gravity manages to sculpt the universe. What is it that we actually know for certain? Science doesn't just offer conclusions. It encourages us to pose even more profound questions. Throughout this discussion, we will investigate how light, the very energy source that brightens our world, has been crucial for solving the universe's greatest riddles. But were you aware that light can act as both a wave and a particle? For centuries, this paradox has captivated scientists, leading to breakthroughs that have completely reshaped our comprehension of physics. In its most fundamental state, light serves as a conduit between the tangible world and the realm of abstract thought. As we venture further, it's fascinating to think about how the simple light bulb did more than just illuminate our homes. It ignited a revolution in our understanding of reality. What if I were to tell you that this humble device was a key catalyst in the emergence of quantum mechanics? For a very long time, classical physics appeared to have all the answers, but the arrival of artificial lighting revealed entirely new dimensions of knowledge. When we picture light, our minds often conjure an image of a straightforward beam that enables vision. However, concealed beneath this apparent simplicity is a complex interplay of particles and waves that defies our everyday intuition. It's much like admiring the tranquil surface of a lake while having no idea of the hidden depths below. Light, much like that lake, possesses a profoundness that only a few have dared to investigate. Consider for a moment the link between an object's temperature and the color of the light it emits. Why is a flame red or blue based on how hot it is? This very puzzle became the launching point for a scientist named Max Planck, who soon found himself at the heart of debates that would forever alter the trajectory of physics. His search for a solution led him to discover that light is not just a wave, but also possesses a quantized nature, meaning it exists in discrete packets. This marked the beginning of what came to be known as the ultraviolet catastrophe, a term that perfectly captures the turmoil that ensues when established knowledge collides with the profoundly unknown. As we proceed, it's vital to acknowledge that light is more than just a physical event. It's also a bridge to our emotions and philosophical thoughts, connecting us to the universe and prompting us to contemplate our place within it. But what occurs when we start to challenge the fundamental essence of light? The photoelectric effect stands as a prime illustration of how light can confound our expectations. How is it possible for something as intangible as light to actually generate electricity? Our exploration doesn't stop there. The dual identity of light, its remarkable capacity to be a wave one moment and a particle the next, ushers in a new phase of our story. Albert Einstein, the very person who transformed our concepts of space and time, immersed himself in this puzzle. The manner in which a single photon can behave in completely different ways based on its circumstances is something that continues to leave us in awe. What does this duality tell us about the very structure of our reality? Now, let's picture an experiment that almost feels like a performance of magic. The double-slit experiment is one of quantum mechanics' most mind-bending demonstrations. When you shoot electrons toward a barrier with two slits, they can act like waves and produce an interference pattern on the other side. Yet, the moment you try to observe which slit they pass through, the electrons behave like distinct particles. How can this be? Is it possible that the simple act of looking changes their behavior? This very question brings us to the Copenhagen interpretation, a framework where quantum reality reveals itself in ways that seem to defy conventional logic. As we explore quantum entanglement, the connection between particles grows even more bewildering. Can two particles truly be linked instantaneously, no matter how much distance separates them? This idea directly confronts our conventional notions of space and time, prompting deep questions about reality's underlying nature. Bell's theorem was formulated in an effort to resolve these enigmas. Through a combination of rigorous experiments and complex equations, the essence of quantum reality was probed. Yet this exploration seemed to create more questions than it answered. Science thus reveals itself as a voyage of discovery, where every new finding simply points us toward even vaster, unknown horizons. The notion that our perceptions might be constrained by our present knowledge is both thrilling and deeply unsettling. In this way, our journey shows that quantum mechanics is not merely a branch of physics, but a portal into the nature of existence itself. As we continue, we'll see how these abstract ideas have concrete effects on everyday life, influencing everything from the way birds navigate to how we perceive smells. The true magic of science is its power to unite the microscopic and the macroscopic, the simple and the complex, dissolving the lines between what we think we know and what remains to be discovered. This expedition through the realms of light and quantum mechanics is merely a starting point. Science is an open invitation to explore, to question, and to stand in awe of the universe. As we delve into each of these subjects, it's important to remember that every new discovery represents one more step toward understanding the world that surrounds us. The simplicity concealed within the universe's complexity is waiting, ready to be uncovered at every turn of our journey. The story of light is among the most captivating in all of science, with an influence that has proven both deep and lasting. For centuries, light was perceived as something almost supernatural, a mystery that thinkers from Aristotle to Newton tried to solve. Yet, it was the humble light bulb that truly began to alter our comprehension of the cosmos. Could you have imagined that the simple act of lighting a room would ignite a fundamental revolution in physics? When Thomas Edison secured the patent for his light bulb in 1879, he did more than illuminate homes and city streets. He also sparked a fire in the minds of scientists. Light, which had long been treated as just a visual wonder, was now being recognized as a form of energy to be studied and controlled. This created a profound change in the way we perceived the physical world, and led to discoveries that forced a major reconsideration of what we knew about light, raising one particularly vexing question. How does an object's temperature determine the color of the light it gives off? This puzzle, which seemed so straightforward, turned out to be an immense challenge, and the German physicist Max Planck found himself at the very center of it. While investigating black-body radiation, he discovered that the light being emitted did not conform to existing theories. The phenomenon, which became known as the ultraviolet catastrophe, directly contradicted the core assumptions of classical physics. To solve this, Planck proposed that energy wasn't continuous, but existed in discrete packets or quanta. an idea that was initially met with disbelief, but began to paint a picture of a far stranger universe than we had imagined. In the quest for clarity, another legendary figure entered the scene: Albert Einstein. His groundbreaking work on the photoelectric effect demonstrated that light, in addition to its known wave-like properties, also behaved as if it were made of particles. For Einstein, this duality wasn't merely a confusing riddle, it was a gateway to entirely new scientific frontiers. How could something as seemingly intangible as light possess such a contradictory dual nature? The notion that light could act like a wave at one moment and a particle the next compelled many scientists to fundamentally question the nature of reality itself. This very question led directly to the development of quantum mechanics, a theory that blurred the lines between certainty and the unknown. A pivotal demonstration of this new worldview came from the renowned double-slit experiment, which showed that electrons behave as particles only when you're looking at them, but act like waves when you are not. How could the simple act of observation dictate the behavior of a fundamental particle? This bizarre outcome gave rise to the Copenhagen interpretation, which proposes that quantum reality is fundamentally shaped by the act of our observation. It was in this arena that two titans of science, Albert Einstein and Niels Bohr, engaged in a profound debate. Einstein championed a universe governed by deterministic laws, while Bohr argued for the inherent uncertainty of the quantum world. The clash between these two perspectives would go on to shape our modern understanding of the universe. As we venture further into the quantum realm, we encounter ideas that challenge our intuition even more, such as quantum entanglement. This phenomenon describes a situation where two particles can become linked in such a way that they influence each other instantly, no matter how vast the distance between them. Could this mean that information is capable of traveling faster than the speed of light? Bell's theorem was developed as a way to probe these questions, using mathematical proofs and experiments to either confirm or deny these strange features of quantum reality. Would scientists finally resolve the enigma that had perplexed the scientific community for so long? Groundbreaking experiments carried out by physicists in Berkeley during the 1970s not only supplied some answers, but also captured the spirit of that transformative era. At a time when culture was challenging established norms, science was similarly pushing the boundaries of what was thought possible. The pioneering work of Clauser and Aspect became crucial in confirming the bizarre, non-local nature of the quantum world. However, their discoveries didn't just close a chapter in physics. They opened a host of new questions about the very fabric of reality. For us as human beings, what does it truly signify that the subatomic world operates in ways that are completely contrary to our everyday intuition and experience? Ultimately, every one of these investigations forces us to contemplate our own place within the cosmos. Light, which started as a simple visual experience, has guided us toward a much deeper comprehension of reality itself, uncovering astonishing links between quantum mechanics and the very processes that define our existence. Are you prepared to continue exploring the mystery that envelops us? The answer could transform your view of the world forever. The relationship between an object's temperature and the color of the light it emits has captivated scientists for centuries. But what happens when logical deduction runs into a complete dead end? During the 19th century, Max Planck became a trailblazer in trying to decipher this connection, a story that starts with a fascinating puzzle. Why do objects change their color as they get hotter? Imagine a piece of bread in a toaster. It begins pale, but with increasing heat it becomes a crisp golden brown. What exactly is occurring during that transformation? As Planck dedicated himself to finding a solution, he ran into a formidable obstacle known as the ultraviolet catastrophe. This term describes a major failure in the physics of his day, where the accepted models were unable to account for the radiation from black bodies, idealized objects that absorb all incoming light. In essence, when an object was heated, the color it produced did not align with the expected logic, and the experimental data seemed to violate the laws of classical physics. As Planck delved deeper, he understood that a completely new perspective was needed, leading to his revolutionary conclusion. Energy is not emitted in a continuous flow, but in small, distinct amounts, he named quanta. This idea astonished his contemporaries. How could energy behave so strangely? The concept that energy exists in discrete units was a groundbreaking notion that established the very basis for what we now call quantum mechanics. This story, however, did not conclude there, as Planck soon confronted a significant puzzle. His groundbreaking discovery ran contrary to the most foundational principles of physics, raising a critical question. Could light, which was universally understood to be a wave, also exhibit the characteristics of a particle? It suggested that light possessed a dual identity, like a quantum superhero capable of assuming multiple forms, an idea that ignited intense debate and unlocked a new way of perceiving reality. In this environment, Max Planck's intellectual struggle acted as the very engine for a scientific revolution. The physics community was presented with a stark decision, either to hold on to the classical models or to accept a reality teeming with unexpected complexities. This pursuit of understanding propelled numerous scientists into a domain where conventional intuition was no longer a reliable guide. The relationship between an object's temperature and the color of light it emits became a powerful illustration of how curiosity can successfully challenge the established order. Planck was doing more than simply searching for a solution. He was pioneering an entirely new paradigm for conceptualizing light and energy. The influence of his work permeates our everyday existence, from the technology we depend on to our contemporary grasp of the physical world. His journey reveals that science is not merely a collection of formulas and laws, but rather a profound adventure in which each new insight can open up a cascade of further inquiries. What if you were to perceive science not as a repository of definitive answers, but as a perpetual exploration of the unknown? Adopting this perspective could fundamentally alter the way you interpret the world around you. Planck's predicament serves as a potent reminder that even the most deeply entrenched truths can be questioned, and that intellectual inquisitiveness is absolutely vital for the advancement of knowledge. His story is an invitation for you to challenge your own conceptions of the universe and to stay receptive to fresh ideas, regardless of how unconventional they might initially appear. The investigation into the link between temperature and color did more than just revolutionize physics. It also demonstrated that a sense of wonder and uncertainty lies at the very core of scientific endeavor. Every time you flip a light switch, you are witnessing the product of centuries of scientific investigation. Planck's story is a single, crucial thread woven into the immense and intricate fabric of human knowledge. Ultimately, science is a voyage without a final destination, and the questions born from his discoveries are guiding us toward the next great frontier of understanding. The profound mystery of how light and electricity are connected has long captivated the minds of scientists and thinkers. What is the mechanism that allows a simple beam of light to produce an electrical current? To grasp this, you must examine the phenomenon known as the photoelectric effect. In the early 20th century, this effect posed a significant puzzle for physicists, directly contradicting the prevailing ideas about the fundamental nature of light. Imagine you are in a completely dark space and you switch on a lamp. As light floods the room, everything becomes visible. But what is truly occurring at a microscopic level? Light is not simply a wave propagating through space. It possesses a much more fascinating quality. It is composed of minuscule packets of energy known as photons. These incredibly small particles act like messengers, each carrying a specific amount of energy. And this is where the process becomes truly remarkable. When light illuminates certain materials, particularly metals, these photons can collide with the electrons present on the material's surface. If a photon has enough energy, it can actually transfer that energy to an electron and knock it free, which in turn sets an electric current in motion. This discovery was not just compelling, it represented a fundamental shift in how we comprehend the laws of physics. So what did this mean for the established understanding of light? By the end of the 19th and the start of the 20th centuries, the wave theory of light was firmly accepted. The discovery of the photoelectric effect, however, created a significant paradox for scientists. If light were exclusively a wave, it was difficult to explain how it could dislodge electrons with such direct impact. It was at this juncture that a young physicist named Albert Einstein appeared, and his insights would permanently alter our perception of light. Einstein put forward the radical idea that light could exhibit the properties of both a wave and a particle simultaneously. This concept, which came to be known as wave-particle duality, was nothing short of revolutionary. Picture light as being similar to a wave moving across the ocean, but at the same time behaving like a solid billiard ball striking another. This dual nature would soon become a foundational element of quantum mechanics, though it was met with considerable skepticism by many in the scientific community at first. Despite the initial resistance, a series of experiments began to validate Einstein's theories. As more research was performed, the evidence became undeniable that light indeed has both wave-like and particle-like characteristics, forcing a radical revision of traditional physics. This led to a complete transformation in the way scientists conceived of the universe. The relationship between light and electricity also encourages you to consider your own interaction with the world. Every time you use electric light, you are directly benefiting from the photoelectric effect. The practical applications of this principle are widespread in modern technology. From the initial invention of the light bulb to the sophisticated devices you use today, the photoelectric effect has been instrumental in the development of technologies like solar panels and digital cameras. Think about a solar panel. When sunlight strikes its photovoltaic cells, photons dislodge electrons, which generates an electrical current. This process serves as a perfect demonstration of how a scientific principle can fundamentally reshape our daily lives, transforming a laboratory curiosity into a critical source of renewable energy. This inherent curiosity is not limited to scientists. You have a deep, intrinsic relationship with light as well. When you glance at the sky and see the sun shining, you are witnessing the very same source of energy that fuels our modern devices. Each time you feel the sun's warmth on your skin, you are having a direct physical experience with the consequences of the photoelectric effect, connecting you to one of the most fundamental principles of the cosmos. This connection, however, reaches far beyond the physical realm, urging us to question the fundamental fabric of reality itself. If light can exist as both a particle and a wave, what other elements of our universe might share this kind of duality? It's possible that many things we accept at face value are significantly more intricate than they first appear. As we delve into the relationship between light and electricity, we enter a domain where scientific inquiry and philosophical thought merge. The photoelectric effect isn't just a physical process. It stands as a testament to the fact that reality is frequently stranger than our imaginations can conjure, inviting us to look past the surface and appreciate the multiple layers of meaning in the world around us. Have you ever stopped to consider how something as ordinary as light can have such a transformative effect on our comprehension of the universe? In its most basic form, light is simultaneously a wave and a particle, a concept that seems contradictory. How can one entity possess two distinct identities at the same time? The resolution to this puzzle is found in the fascinating duality of light, a principle that completely upended the world of physics. Throughout history, scientists have strived to decode the enigma of light, but it was a figure in the early 20th century who would permanently alter our view of this phenomenon: Albert Einstein. Einstein's work not only defied the established scientific beliefs of his era, but also constructed the very foundation of what we now call quantum mechanics. But what exactly propelled him toward this revolutionary insight? The crucial clue was hidden within the photoelectric effect, where he observed that light, upon striking a material, could dislodge electrons. This particular outcome was impossible to explain if light was treated exclusively as a wave. It's truly remarkable to think that this single observation earned Einstein the Nobel Prize and forced the scientific community to fundamentally rethink its understanding of light. At that time, the question on everyone's mind was, how can something be both a wave and a particle? The solution to this enigma introduces one of quantum mechanics' most captivating ideas: wave-particle duality. To help you visualize this, imagine you are at a concert with your eyes closed. You experience the music as a wave of sound washing over you. Yet, you can also perceive that sound as a series of individual notes, each with its own unique identity. Light operates in a similar fashion, capable of propagating like an expanding wave while also interacting with matter as a stream of distinct particles called photons. This concept proved to be a pivotal moment in the history of science, not just because it deepened our understanding of light, but because it unlocked new questions about the nature of reality. What does it really mean to observe something? Can our act of perception alter the state of the object being observed? These are the kinds of profound questions that continue to fascinate us and challenge our very sense of existence. And the journey into the quantum world doesn't stop with light. This principle of duality suggested that everything at this microscopic level is interconnected in ways that defy our classical, everyday intuition. Einstein's legacy, along with the contributions of his peers, has done more than just reshape physics. It has planted the seeds for our modern technological world. Are you aware that many of the devices you use daily, from lasers to semiconductors, are built upon these quantum principles? Light, in its most fundamental state, has become an essential tool in our ongoing pursuit of knowledge and discovery. This naturally leads to the question, what other secrets does quantum mechanics have yet to reveal? As research progresses, we find that the duality of light is more than just a peculiar phenomenon. It's a gateway to a universe filled with untapped potential. The implications of this duality extend beyond the laboratory, influencing how we perceive life itself and our relationship with the surrounding world. Ultimately, the dual nature of light serves as a fitting metaphor for existence, reminding us that things are rarely as they initially seem, and that reality is often far more nuanced than our senses suggest. In this immense cosmos, governed by unfamiliar rules, we can find an unexpected elegance within the complexity of simple things. The next time you switch on a lamp, take a moment to remember that you are witnessing a phenomenon that redefined science, a process where a photon may have just liberated an electron to illuminate your space. Indeed, the notion that an electron can behave as both a particle and a wave is so strange that it feels like it belongs in science fiction. So how did scientists ever arrive at such a mind-bending conclusion? The answer is found in a landmark experiment that fundamentally challenged our perception of the universe, the double-slit experiment. Despite its simple setup, this experiment uncovers some of the deepest and most profound secrets about the true nature of quantum reality. In the elegant dance between wave and particle, we find a mirror to our own existence, a place where the questions we ask are just as vital as the answers we find. Consider a scenario where you launch a tiny object, such as a ball, toward a barrier containing two vertical openings. As a particle, you'd anticipate it would travel through one slit or the other, leaving a simple pattern of two impact marks on the screen behind it. The story takes a fascinating turn, however, when you replace the ball with electrons. When this double-slit experiment is performed with these subatomic particles, the outcome is far more baffling than you might imagine. Initially, scientists presumed that electrons would behave just like miniature balls, passing through either the left or the right slit. Instead, upon examining the results, they found that the electrons formed an interference pattern on the screen, much like waves rippling across a pond. This startling discovery implied that, impossibly, each electron was somehow passing through both slits at the very same time. How could something so small and seemingly solid exhibit the properties of a wave? The mystery deepens considerably when researchers attempt to observe which path an electron takes. By placing a detector at one of the slits to determine which one the electron goes through, the wave-like interference pattern completely disappears. The electrons immediately revert to behaving like particles, creating two distinct bands on the screen corresponding to the slits. This suggests that the simple act of observation fundamentally alters the behavior of these tiny entities. This phenomenon raises profound questions about the very fabric of reality itself. Could it be that the quantum world is directly influenced by our observation of it? Imagine being at the cinema and choosing to look away just as a pivotal scene is about to happen. In this strange quantum analogy, your decision to watch or not could literally change the movie's plot. In the quantum realm, observation wields such incredible power that it can dictate the outcome of an experiment. This particle-wave duality forces us to reconsider our most basic assumptions about the world. If electrons can exist as both particles and waves, what does that reveal about our universe? The discovery challenges the notion that reality is a fixed and objective state, suggesting instead that it may be in a constant state of flux, dependent on how we interact with it. For Albert Einstein, a man who believed in certainty, reality existed independently of us, operating like a predictable clockwork mechanism whether we were watching or not. This very interpretation ignited one of the most significant debates in scientific history between Albert Einstein and Niels Bohr. Einstein, with his deterministic worldview, resisted the idea that randomness and uncertainty were fundamental aspects of physics, famously stating that God does not play dice. In contrast, Bohr argued that the quantum nature of reality means we are fundamentally limited in what we can know about a system at any given moment, and that our observation is an inseparable part of the result. What makes this experiment even more compelling is its link to the concept of quantum entanglement. Picture two electrons that are entangled. This means that regardless of the distance separating them, a change to one will instantaneously influence the other. It's as though they maintain a hidden connection, enabling them to communicate across otherwise unimaginable expanses. This bizarre property directly challenges our classical ideas of space and separation. The double-slit experiment, therefore, is far more than a simple laboratory demonstration. It offers a profound glimpse into the nature of reality itself. It prompts us to reevaluate our assumptions and entertain the possibility that the universe is far stranger than we have ever conceived. The true importance of this experiment extends beyond its theoretical implications and into its practical value for modern innovation, from quantum computing to advanced cryptography, where these quantum principles are actively shaping the future of technology. The wonder of this experiment is a powerful reminder that the universe is filled with mysteries yet to be unraveled. It encourages us to embrace uncertainty and to continue exploring the vast unknown. As we persist in our quest for answers, it becomes essential to maintain an open mind and a readiness to question everything we believe we know. After all, at the very core of all scientific progress lies an insatiable curiosity, the engine that drives all knowledge. Without an observer, particles exhibit wave-like properties, generating a distinct interference pattern on a screen placed behind them. However, the moment you choose to watch which slit an electron passes through, that interference pattern completely vanishes, and the particles behave like tiny, solid pellets. This raises a fundamental question. How can the simple act of looking at something alter its core behavior? The Copenhagen interpretation offers a compelling answer, suggesting that quantum reality is not fixed, and that observation doesn't just passively record what's there, but actively influences the outcome. So, does this imply that you are literally constructing your own reality? The truth is far more nuanced. We are dealing with a quantum realm that operates outside the familiar rules of classical logic, which can be deeply disorienting. It's easy to feel as if we are encountering a form of quantum magic, and for many who try to grasp these concepts, it's like venturing into a world of fantasy. And yet, this seemingly enchanted domain has produced incredibly tangible and powerful results in our world. Indeed, the principles of quantum mechanics have laid the groundwork for innovations like quantum computing and quantum cryptography, technologies with the potential to completely revolutionize our lives. This strange new physics was also at the center of the historic debates between Einstein and Bohr, which represented not just a clash of personalities, but a profound dialogue between two opposing worldviews. Bohr, with his more fluid, probability-based perspective, became the champion of the Copenhagen interpretation, whereas Einstein's orderly mind flatly rejected the idea that pure chance could be a fundamental feature of the universe. This core conflict remains just as relevant today, with scientists continuing to probe its deep implications. Does this leave us caught in a quantum paradox? The friction between observation and reality compels you to question how you perceive your surroundings. Every time you observe something, are you altering its very nature? Science suggests that the answer is yes. The Copenhagen interpretation invites you to see your perception not as passive reception, but as an active engagement that helps shape what we define as real. It is a truly astonishing thought that on the most fundamental level, the universe might be far more interconnected than we typically believe. The act of observation transforms from a simple glance into a powerful interaction that can mold the essence of matter itself. This realization leads to a profound inquiry. If your choices and actions can shape reality, what does that signify for your day-to-day existence? The Copenhagen interpretation has ultimately paved the way for a new comprehension of our world, prompting a deep reflection on the creative power of observation in our lives. What if I were to tell you about a cosmic phenomenon that defies all our conventional ideas of distance and connection? Picture two particles, separated by thousands of kilometers, yet capable of influencing each other in an instant. This effect is known as quantum entanglement, and it stands as one of the most baffling and thrilling aspects of quantum mechanics. In our daily experience, we naturally assume that objects are separated by the space between them. A ball thrown across a room surely has no impact on something on the other side, right? Quantum entanglement, however, shatters this intuitive assumption. A pair of entangled particles behaves as if linked by an unseen cord, so whatever affects one is immediately mirrored in the other, no matter how vast the distance separating them. To grasp how this is possible, think of a pair of gloves. If you discover a left glove in one box and a right one in another, you know they belong together, even if the boxes are miles apart. In the quantum world, though, particles lack a fixed identity until measured. It's as if those gloves could transform at the very instant you look at them, thereby revealing their nature. This strange behavior was first outlined by Albert Einstein, who famously called it spooky action at a distance. He found the concept of entanglement so bizarre that he refused to accept it as a genuine feature of nature, believing some hidden, deeper explanation must exist. Yet, decades of experiments have confirmed that entanglement is not just a theoretical oddity, but a verifiable fact of our universe. In a typical experiment, two particles are generated as a pair and then sent in opposite directions, and when you measure the state of one, you instantly determine the state of the other, even if it's light years away. This phenomenon opens up incredible possibilities in fields like quantum computing and cryptography, potentially enabling instantaneous communication across galaxies. But what does it suggest about the nature of reality itself? If information can travel between particles without any delay, does it mean that space and time are not the absolute constants we once thought they were? Some scientists propose that entanglement points to a universe that is far more interconnected than we can easily imagine, suggesting that perhaps we aren't as separate as we feel. In our everyday lives, we are conditioned to see things as individual and distinct entities. Quantum entanglement, however, encourages a more holistic vision of the cosmos, one where all particles might be woven together into a single, interconnected web that transcends our classical understanding. This concept has profound implications extending from physics into philosophy, prompting us to wonder if such entanglement could even relate to the deep emotional bonds we form with one another. It's possible to conceive of our relationships as being intertwined in ways that transcend the purely physical, and quantum science compels us to challenge our assumptions and embrace new possibilities. The study of entanglement is not merely fascinating, it stands at the vanguard of technological innovation. Breakthroughs in quantum computing, which are built upon the principles of entanglement, hold the promise of transforming how we process information, leading to computers that can solve monumental problems in an instant and unlock new frontiers in artificial intelligence and complex system simulations. However, the very nature of entanglement also presents us with significant ethical questions. If we gain the ability to transmit information instantaneously across any distance, what measures can we put in place to ensure this power is wielded responsibly? It forces us to ask whether we are truly prepared to comprehend and manage the immense capabilities that this knowledge could unlock. In its relentless pursuit of the universe's secrets, science also calls upon us to reflect deeply on the consequences of our discoveries. As we advance toward a future where quantum mechanics could become a fundamental part of our everyday existence, the concept of entanglement serves as a powerful reminder that the universe is a place of profound mystery and complexity. It challenges our most basic ideas about connection and distance, suggesting that within this enormous cosmos, we may be far more interconnected than we ever dared to imagine. Perhaps this hidden linkage is an integral part of the beauty and wonder of being. Quantum entanglement provides a new lens through which to view the world, inviting you to consider that the boundaries we perceive might be more illusory than we believe. Throughout this scientific journey, we arrive at a crossroads where curiosity and awe become one, opening a gateway to a future filled with incredible discoveries. So, the next time you ponder the meaning of distance, remember that at the most fundamental level, everything is connected. And this is only a glimpse of what quantum mechanics has in store. Have you ever stopped to truly question what constitutes reality? For generations, scientists have grappled with this enigma, and one of the most compelling landmarks in this quest is Bell's theorem. This theorem acts as a crucial bridge between the strange world of quantum mechanics and the familiar reality of our daily lives. But to understand its significance, we first need to grasp what Bell's theorem actually is. To illustrate, imagine you have a pair of gloves, one for the left hand and one for the right, and you seal them in two separate boxes. You then mail these boxes to two different friends who are separated by hundreds of kilometers. The moment one friend opens their box and sees a right-handed glove, they know with absolute certainty that the other friend has the left. While this seems perfectly logical in our world, in the quantum realm, the situation is far from straightforward. At the heart of Bell's theorem lies a concept known as non-locality. This principle suggests that particles at the quantum level can become so fundamentally linked that the state of one can instantly affect the state of another of the other, no matter how vast the distance between them. The profound question is, how could this possibly work? Bell's theorem posits that if quantum mechanics is an accurate description of the universe, then we are forced to accept that some natural phenomenon exists that completely defies our classical understanding of cause and effect. For many years, physicists have dedicated themselves to either proving or discrediting the predictions of Bell's theorem. The difficulty of this task stems from the fact that quantum mechanics, at its core, doesn't operate according to the deterministic rules we are used to. Instead of following a predictable path, particles exist in a state of probabilities. This leads to the staggering idea that what we perceive as solid reality might be nothing more than an illusion, our brain's interpretation of a far more intricate and hidden truth. The experiments designed to put Bell's theorem to the test aimed to determine if particles could truly be entangled, linked in a way where the state of one instantaneously dictates the state of its partner across great distances. It's an astounding notion to consider that two particles could communicate in an instant, almost as if they were a pair of friends sharing telepathic thoughts. Yet this phenomenon appears to have no simple, intuitive explanation within our everyday experience. During the 1970s, a series of experiments conducted by a team of scientists seemed to validate the predictions of Bell's theorem. The outcomes demonstrated that particles were indeed entangled, with their properties correlating in a manner that defied the logic of classical physics. This was a powerful indication that there is something more to reality than what we can see or directly measure. Still, some critics contended that these results might be explainable through alternative theories, which sparked intense and ongoing debates within the physics community. The central question that arises from this is, what are the true limits of our comprehension of reality? Some thinkers propose that Bell's theorem suggests our perception of the world is inherently restricted, and that there may be other dimensions of existence that we simply lack the ability to perceive. The very idea that our observations could influence quantum reality implies that consciousness might play a crucial role in the creation of what we call truth. Could it be that the human mind is somehow an active participant in shaping the universe? In a world where physical distance can become irrelevant, quantum entanglement invites you to fundamentally redefine your concept of connection. This makes Bell's theorem not just a cornerstone of modern physics, but also a catalyst for profound philosophical inquiry. It compels us to challenge our ingrained assumptions about what it means to be an individual and what separates one thing from another. As our exploration continues, it's clear that the theorem is a window into a much deeper understanding of the cosmos. Bell's theorem forces us to reconsider our foundational ideas about time, space, and causality, with each new discovery bringing us a little closer to understanding what it means to exist in this universe. We can see how its influence has extended far beyond physics, shaping how we confront questions of existence and reality itself. The ongoing debates surrounding quantum entanglement have inspired philosophers, writers, and artists, fostering a vital and enriching dialogue between the realms of science and culture. The theories underpinning quantum mechanics can often appear to be an impenetrable maze of complex concepts. What if I were to tell you, however, that it all essentially boils down to a straightforward game of connections? Back in the 1970s, a team of physicists in Berkeley undertook the challenge of testing Bell's theorem, a proposition that held the promise of illuminating the enigma of quantum reality. How did they find the courage to question everything we assumed we knew about the cosmos? Imagine for a second that you possess a standard coin. When you toss it, the outcome will be either heads or tails, correct? Now, envision quantum mechanics as a kind of enchanted coin. This coin doesn't have to choose between heads or tails. Instead, it can exist in both states simultaneously, right up until the moment it is observed. In this way, Bell's theorem directly confronts our most basic assumptions about the mechanics of the world, forcing us to ask whether this phenomenon is a mere trick of perception, or if something far more profound is happening. Now, let me ask you this. What would you think if I said that two particles could be intertwined in a manner that defies all we understand about space and time? The narrative we're about to delve into centers on experiments by two brilliant physicists, John Clauser and Alain Aspect, who put Bell's theorem to the test. Their work encourages us to see the quantum realm from a completely new perspective, one where distance is irrelevant and the link between particles can be instantaneous. Think of it like having a pair of gloves, one for the left hand and one for the right. The experiments undertaken in Berkeley were akin to a treasure hunt through the quantum domain. Scientists embarked on a quest to determine if particles could truly be entangled, sharing information with each other instantly, no matter how vast the distance between them. Picture having two friends who, regardless of their separation, are always aware of what the other is thinking. The concept is astonishing, isn't it? This quantum entanglement implies that on a foundational level, the universe is interconnected in ways we could never have previously conceived. To test Bell's theorem, the physicists in Berkeley adopted an exceptionally creative strategy. Rather than merely observing individual particles, they chose to analyze their behavior in pairs. And in doing so, they started to uncover something extraordinary. The outcomes they recorded could not be reconciled with the principles of classical physics. How could it be that these particles seemed to be communicating with one another across the void of empty space? And what were the implications of this for our perception of reality? The atmosphere in Berkeley during those years was just as dynamic and inventive as the experiments themselves. It was the era of counterculture, a time when revolutionary concepts permeated the air and science began to merge with art and philosophy. The scientists viewed themselves as artists, sculpting masterpieces from equations and experimental setups. It's almost as if the art of science and the rhythm of life converged to unlock the universe's most guarded secrets. Some of these experiments required the use of lasers and particle detectors to log the interactions of light, and with every measurement taken, the results appeared to defy all logical expectations. A heated debate began over whether these particles were genuinely interconnected or if their behavior only gave that impression. This led to the pivotal question: could these observations simply be the result of random chance, or was there a deeper, more enigmatic connection dictating their actions? Even physicists like Einstein found it difficult to embrace the idea that reality could be so bizarre, famously asking, "Does God play dice with the universe?" Well, the answer to that question remains elusive. One thing became certain. Every single experiment performed in Berkeley left an unmistakable imprint on our comprehension of quantum mechanics. Their work not only validated Bell's theorem, but also flung open the doors to a new understanding of the cosmos, with each result echoing through the corridors of science and expanding the horizons of what we deemed possible. This period also highlighted the link between science and society, as the quantum experiments were more than just a pursuit of truth. They mirrored the spirit of a generation that questioned established conventions. Quantum mechanics itself became a powerful symbol for the search for freedom and authenticity in a world often constrained by unyielding rules. It prompts the question: could the ultimate purpose of science be to ignite our curiosity and creativity? Ultimately, the findings from these experiments have sparked profound reflections on the very nature of reality. If quantum entanglement is a fundamental truth, what does that suggest about our own identity and our place within the universe? The notion that we are all interconnected in some manner resonates with numerous philosophical and spiritual beliefs throughout human history, suggesting there might be a hidden wisdom within this entanglement. This research didn't just challenge classical physics. It invited us to reconsider our entire relationship with the cosmos. In this light, Bell's theorem serves as a potent reminder that science and art can beautifully intertwine in their mutual search for meaning. As our technology progresses and experiments grow ever more sophisticated, we are bound to continue uncovering the secrets of quantum reality. While a complete understanding of entanglement and non-locality may still be far off, Bell's theorem remains a captivating mystery that challenges us to think beyond the visible world and reminds us how much there is still left to discover. So the next time you gaze up at the night sky, take a moment to remember that every star and every particle is connected in ways we are just beginning to comprehend. The lingering questions about reality and consciousness will undoubtedly continue to fuel the curiosity of future generations of scientists and thinkers in our ongoing quest to unravel the secrets of the cosmos. By exploring Bell's theorem, we enter a domain where science, philosophy, and art all intersect. And who can say what other wonders await us in the vast ocean of quantum mechanics? Imagine you separate two connected objects by 1,000 kilometers. Upon opening one, the other's shape becomes instantly known. This simple thought experiment provides a glimpse into quantum entanglement, a principle where particles, once linked, can communicate across immense distances. The question of how this is possible delves into the fundamental fabric of reality, a mystery that physicists Clauser and Aspect dedicated themselves to unraveling. During the 1970s, Clauser undertook a pioneering experiment in Berkeley, California, with the aim of testing a highly debated aspect of Bell's theorem, the idea that entangled particles could influence one another instantaneously, no matter how far apart they were. You can just feel the profound tension and excitement that must have filled the lab as he readied a test that held the potential to fundamentally alter our view of the physical world. Clauser's work centered on measuring the specific properties of paired, entangled particles. When one particle was observed to be in a particular state, its distant twin would immediately adopt that very same state. The truly mind-bending part was this instant correspondence. The moment one particle was measured, the other seemed to acquire this knowledge without any delay. How could information possibly travel between them faster than the speed of light? The most startling revelation occurred when Clauser's experimental data started to confirm the predictions of quantum mechanics, suggesting that reality is far less straightforward than we had assumed. In a universe that we perceive as governed by clear cause and effect, these quantum particles were exhibiting bizarre and counterintuitive behaviors. This prompted a profound reevaluation of our understanding of the cosmos, which Albert Einstein further solidified in 1982, with more refined experiments that not only corroborated Clauser's results and Bell's theorem, but also launched the entire field of quantum computing. But what is the human significance of all this? The way quantum entanglement seems to defy our conventional understanding of space and time inevitably leads to deep philosophical inquiries. If two particles can be perfectly connected across an empty void, what does that imply about the nature of reality itself? Could it be that the universe is far more interconnected than it appears on the surface? The consequences of these experiments extended far beyond physics, creating ripples in the world of philosophy. For some thinkers, quantum entanglement points to a more holistic reality where everything is fundamentally linked. Others speculate that it might offer a gateway to entirely new theories about consciousness itself, potentially providing a framework to address questions that have captivated humanity for ages. Furthermore, quantum entanglement is no longer just a theoretical curiosity. It has found practical uses in today's technology. It is the basis for quantum computers capable of solving incredibly complex problems at unprecedented speeds, and for quantum cryptography, which offers a revolutionary method for secure information transfer. It is truly remarkable to consider that a principle of nature so at odds with our intuition could be the very foundation for future technological breakthroughs. When you reflect on the contributions of Clauser and Einstein, you see more than just a scientific advance. You witness a fundamental shift in our entire worldview. The notion that particles can be intertwined in ways beyond our direct perception encourages us to challenge our core beliefs about what it means to be separate and individual. It suggests that on a deeper level, we might all be more connected than we realize. Every new insight in this area adds another piece to the vast quantum puzzle, serving as a powerful reminder of how much remains unknown. The very nature of quantum mechanics is a call to perpetual curiosity, urging us to question established knowledge and remain open to novel ideas. One can only wonder what other marvels lie waiting to be discovered in our immense and enigmatic universe. As we navigate this journey through the strange world of quantum mechanics, it's essential that you hold on to your sense of wonder. Science is a continuous exploration, where each new question is another doorway to discovery. So, the next time you gaze at the night sky and contemplate the universe, remember that there are countless secrets yet to be revealed, mysteries to be solved, and connections that stretch beyond our concepts of time and space. Our adventure is only just beginning. What if I proposed that the birds you see gliding through the air are using quantum mechanics for their long migratory flights? It's a truly fascinating thought. Each year, millions of birds undertake incredible journeys, covering thousands of kilometers with breathtaking accuracy. The question is, how do they navigate so flawlessly across such vast and featureless skies? One of the keys to this amazing feat is a protein named cryptochrome, which is located in the retinas of birds. This light-sensitive protein is central to their navigational sense, as it enables them to actually perceive the Earth's magnetic field through chemical reactions triggered by sunlight. Although this may sound like a concept from science fiction, it is grounded in established science. To understand this, picture yourself in a dark room when a faint light suddenly appears, not only showing you the objects around you, but also giving you a sense of your location. Birds experience a similar process, but for them, the sunlight itself interacts with a quantum system to orient them. The entire mechanism hinges on how cryptochrome responds to light. When a photon strikes the protein, it sets off a crucial transformation. This interaction results in the creation of a pair of entangled electrons, which means that even though they are separate, their states are instantly and inextricably linked. It's as if they share a private, instantaneous line of communication that is unaffected by distance. For the birds, this quantum entanglement allows them to process information from the Earth's magnetic field, effectively using it as a biological compass to guide their long-distance travel. It seems as though birds possess an innate global positioning system, enabling them to sense their orientation in relation to magnetic north. This ability allows them to navigate with astonishing precision, even when facing harsh weather or traversing unknown lands. For many avian species, this sense has been absolutely vital for their survival throughout the long course of evolution. These migrations are not simply journeys. They represent a fundamental necessity. Birds undertake these massive travels to secure food sources, find mates for reproduction, and escape from severe climatic extremes. The capacity for exact navigation has proven to be a critical trait favored by natural selection, and it appears quantum mechanics has been instrumental in its development. But what happens if we shift our point of view to ourselves? Is it possible that humans also harbor latent abilities that are governed by the principles of quantum mechanics? While we are a long way from comprehending the full scope of quantum effects on our biology, researchers are starting to investigate how these concepts might extend to other life forms, including us. Just think what it might be like if we could leverage quantum mechanics to augment our own perception of reality. The notion that a molecule as minuscule as cryptochrome could lead to such profound outcomes might sound unbelievable, yet it serves as a powerful reminder of nature's remarkable capacity for solving intricate challenges. At the same time, this phenomenon encourages us to consider the deep interconnectedness of all living organisms. Birds, in their migratory flights, aren't just tracing predetermined paths. They are integrating into a vast dynamic network within the greater ecosystem. Their movements have a ripple effect on other species, and their navigational prowess can tip the scales of life's balance across the planet. In this light, quantum mechanics doesn't just teach us about particles and waves. It provides a completely new framework for understanding the world. It urges us to contemplate our own interactions with the environment and recognize how our actions can have consequences that extend far beyond our immediate sight. As our knowledge of how quantum mechanics shapes biology deepens, we find ourselves on the cusp of a new era in science. Birds offer just one glimpse into how these fundamental principles can manifest in the natural world. If the migration of birds truly is rooted in quantum physics, what other astonishing secrets might nature be waiting to share with us? Secrets we have yet to even imagine. So, the next time you happen to see a bird soaring through the sky, take a moment to remember that an entire world of incredible science underpins that seemingly simple flight. Quantum mechanics is far from being a mere abstract theory. It is woven into the fabric of our daily existence, linking all forms of life in ways we are only now starting to grasp. The great journey of birds compels us to think about our own position in the cosmos. What other marvels are waiting to be found? What further enigmas of nature could be solved by looking through the lens of quantum science? The quest for answers is ongoing, beckoning us to venture into the unknown with a spirit of wonder and curiosity. Have you ever stopped to appreciate the sheer complexity of the scents around you? From the rich aroma of morning coffee to the delicate perfume of a spring blossom? Our capacity to perceive smells is a true marvel of biology. But would you be surprised to learn that quantum mechanics may have an unexpected part to play in how we register those fragrances? This line of inquiry brings us to a captivating field that connects physics and biology, known as quantum biology. The experience of smell starts when an object releases molecules that drift through the air and into our nostrils, where they make contact with olfactory receptors inside our cells. But how exactly do these molecules manage to activate a sensation within our brains? It is at this critical point that quantum mechanics may offer an explanation. Consider each scent molecule as a microscopic messenger on a mission to navigate a dense sea of other atoms and molecules, sometimes requiring a bit of a boost to arrive at its final target. Quantum mechanics posits that, on the smallest scales, particles do not behave in the ways we're accustomed to. They don't follow a single, predictable path. Instead, they can exist in many different states simultaneously. This might sound bizarre, but in the quantum realm, it's perfectly normal. So what occurs when one of these scent molecules finally reaches an olfactory receptor? This is where the story becomes truly fascinating. Scientists have put forward the theory that scent molecules might employ a quantum phenomenon known as quantum tunneling to bypass energy barriers. Picture yourself trying to get over a very tall fence. According to classical mechanics, you would need sufficient energy to leap over the top. In the quantum world, however, you might just materialize on the other side without ever making the jump at all. This same principle may enable scent molecules to attach to their designated receptors with much greater efficiency. Quantum tunneling isn't just a theoretical curiosity. Some research indicates this very mechanism could be the reason we are able to detect certain smells at incredibly low concentrations. Essentially, thanks to quantum mechanics, our sense of smell might be vastly more sensitive than we ever thought possible. But what is the connection between this subatomic process and our daily lives? When we smell something, our response is more than just physical. It's also deeply emotional. Different aromas can trigger powerful memories, feelings, and moods. By shaping how we initially perceive these scents, quantum mechanics might be the hidden link that connects the fragrance of a flower to a long-forgotten childhood memory. Isn't it incredible to consider that a physical process at the tiniest level could exert such a significant influence on our emotional world? Moreover, this understanding pioneers a new avenue of research into how smells can guide our decisions and shape our behaviors. Is it conceivable that the chemistry of an aroma, orchestrated by quantum mechanics, could influence our choice of a romantic partner or our preferences for particular foods? This is a frontier that scientists are just beginning to investigate, and the potential implications are enormous. Imagine a future where our grasp of how scents operate at the quantum level allows us to design perfumes that not only smell wonderful, but also actively improve our emotional well-being. Quantum biology isn't just revolutionizing our view of chemistry. It's fundamentally reshaping our understanding of the profound connection between the body and the mind. As our knowledge of quantum biology expands, the question of the quantum world's impact on our daily lives grows ever more significant. The notion that your sensory perceptions might be shaped by the laws of physics is a potent one, prompting a re-evaluation of how you comprehend not only sense, but all sensory input. Quantum mechanics, therefore, isn't just a niche subject for physicists. It's a framework that can deepen our insight into human nature itself, becoming a bridge that connects hard science with personal experience, and inviting you to explore the very reasons behind your feelings. With every new piece of the quantum puzzle we solve, we edge closer to understanding the intricate complexity of both the universe and ourselves. The relationship between physics and biology is a powerful reminder that while the phenomena surrounding us are diverse, they are often interwoven in the most surprising ways. By delving into how quantum mechanics could influence your sense of smell, you open a door not just to new scientific frontiers, but also to a more profound appreciation of your own humanity. The next time you savor the aroma of coffee or a flower, consider that a hidden quantum reality is orchestrating that very experience. Metamorphosis is a captivating natural event, illustrating how life can transform in ways that feel almost magical. Take the tadpole, for instance, a small being that starts its existence in water, perfectly adapted with a swimming body and gills. Yet how does this tiny creature miraculously change into a frog, an animal that leaps on land and breathes air? The mechanism behind this astonishing transformation may be more deeply rooted in quantum mechanics than you might think, with each stage of its development, from egg to adult frog, being meticulously organized. This is where the narrative takes a fascinating turn, as the strange and compelling field of quantum physics may be influencing this biological process. How can something so abstract impact a creature so tangible? The solution could be found in the way a tadpole's cells communicate and cooperate throughout its metamorphosis. It's well understood that at the quantum level, particles can behave in unpredictable ways, interacting in a manner that classical physics simply cannot account for. This suggests cells might not just be responding to chemical signals, but could be using quantum principles to coordinate their actions in a stunning biological dance. The communication network among cells during a tadpole's transformation is much like a symphony orchestra. Every cell plays its part, but they must all perform in perfect harmony for the final composition to succeed. When one cell gets a signal, its resulting action can influence its neighbors, creating a ripple effect. This type of cellular dialogue is not only essential for the tadpole's development, but is also suspected of being tied to quantum phenomena that enable information to be transmitted instantly and with remarkable efficiency. Scientists are now exploring whether the quantum processes within a tadpole's cells might reveal the most fundamental nature of life itself. What if existence, at its very core, operates according to quantum rules that we are only just beginning to comprehend? Such inquiries drive us to investigate not only the development of tadpoles, but the entire framework of biology. It's also captivating to wonder how these quantum principles might extend to other living things, such as a butterfly emerging from its chrysalis, another breathtaking spectacle of transformation that could also harness quantum mechanics. As researchers continue to probe the field of quantum biology, it's becoming clear that the consequences of these findings could be much more extensive than we initially imagined. For instance, some theories propose that quantum mechanics might be the engine behind life's most essential functions, like photosynthesis, the process plants use to turn sunlight into energy. If quantum rules can direct how a tadpole becomes a frog, it raises the question of what other natural marvels might be explained by them. The metamorphosis of a tadpole is far more than a simple physical alteration. It's a voyage that showcases the complexity and elegance of life. Imagine for a second that every cell inside your body is in constant conversation with the others, employing quantum principles to synchronize its functions. While this idea may sound unusual, a growing body of research indicates we are only just beginning to appreciate what it truly means to be alive. The next time you observe a tadpole in a pond or a butterfly in a garden, remember that an unseen realm is at play, where the laws of reality are far more fluid than you might perceive. We are at the very start of a scientific voyage, where every new finding brings us a step nearer to solving the profound enigmas of life and the cosmos. A captivating field known as quantum biology examines how the principles governing the tiniest particles can shape biological functions on a much grander scale. If you've ever asked yourself how living things can carry out such intricate and precise tasks, the answer might just be found in the quantum realm. To grasp this concept, think of a symphony orchestra, where each musician plays a part. But true magic emerges from their harmonious collaboration. Similarly, in the biological world, molecules interact with one another according to incredibly precise rules, much like musicians following a score. Quantum mechanics provides that score, enabling these molecular interactions to unfold with remarkable efficiency and purpose. A prime illustration of this is photosynthesis, the mechanism plants use to turn sunlight into chemical energy. In this process, the leaves act as masterful performers, leveraging quantum mechanics to capture and utilize solar energy with almost no waste. This is achieved through extraordinary quantum phenomena, where electrons behave in unique ways that permit the nearly lossless transfer of energy from one molecule to the next. Another fascinating example lies in the incredible navigational abilities of migrating birds. It turns out that some species can actually perceive the Earth's magnetic field by using quantum mechanics. This system functions like a sophisticated internal GPS guided by a tiny molecule in their eyes that reacts to both light and the direction of the magnetic field, a quantum compass essential for their survival. As our exploration of quantum biology deepens, we are discovering that it may even influence our own senses. Take your sense of smell, for instance, which might rely heavily on quantum principles. When you detect a scent, molecules in your nose are interacting with odor molecules, and it's theorized that a quantum process allows your body to identify these scents far more accurately than by just recognizing their physical shape. Consider the stunning transformation of a tadpole into a frog. Throughout this metamorphosis, the creature's cells undergo drastic reorganization, and it's believed that quantum mechanics could be orchestrating some of these changes. The molecules within these cells must communicate and execute complex decisions about their development, almost as if they are speaking a unique quantum language. This field's reach extends even to the very engine of life, evolution. It is conceivable that the genetic alterations that fuel evolutionary change are themselves influenced by quantum events. This opens up the revolutionary idea that genetic diversity, the very source of adaptation and survival, could be directly linked to quantum principles, with mutations arising from quantum shifts in the molecules of our DNA. This quantum perspective is fundamentally altering our perception of what it means to be alive, suggesting that evolution may not be a linear, predictable sequence, but rather a chaotic dance, directed by the laws of quantum mechanics. We can no longer view biology as merely a set of chemical reactions. We must now account for the intricate ways quantum physics is woven into these life processes. So, what could this mean for the future of medicine, genetics, and biotechnology? By delving further into quantum biology, we may unlock novel methods for treating diseases, enhancing agriculture, and perhaps even gaining a clearer understanding of our own position in the universe. It is an invitation to explore the unknown and to expand our definition of life itself. In essence, quantum biology reveals that life's intricacy is not just a biological wonder, but a quantum one as well. From photosynthesis to your sense of smell, every aspect of the living world is filled with mysteries we are just starting to comprehend. The next time you admire a tree, watch birds in flight, or smell a flower, remember that you may be witnessing quantum mechanics in action, shaping the very fabric of life around you. What makes it possible for plants to be so remarkably effective at this process? The explanation is rooted in a quantum effect known as quantum coherence. You can envision it as a flawlessly synchronized orchestra, where instead of musicians playing their parts separately, every element functions in perfect harmony. In this way, the electrons within chlorophyll act as if they are interconnected, enabling them to travel rapidly through the plant's structure to find the most efficient route for converting light into chemical energy. So, what is the significance of this for us as human beings? It demonstrates that nature has perfected an energy capture mechanism that far exceeds any technology we have created to date. Our machines commonly lose energy in the form of heat, but plants operate differently. Through evolution, they have learned to minimize this energy loss, which makes them incredibly adept at transforming sunlight into the power required for their growth and survival. This level of efficiency stands as a powerful testament to the influence of quantum mechanics within biological systems. Investigating quantum coherence in photosynthesis does more than just deepen our comprehension of how plants harness energy. It also serves as an inspiration for new technological paradigms. Scientists are currently exploring methods to replicate these quantum processes in order to build more effective solar panels and energy systems. By taking lessons from the natural world, we might be on the verge of unlocking innovations that could revolutionize our approach to capturing and utilizing energy. Viewed in this light, photosynthesis is not merely a biological function. It represents a masterclass in quantum efficiency. It serves as a reminder that the world around us is far more intricate than we often acknowledge, and that the principles governing the universe's tiniest particles are essential for sustaining life on this planet. As we delve further into the intersection of quantum mechanics and biology, we continue to uncover the hidden links that make life itself possible. The next time you observe a plant absorbing sunlight, consider that it's not just taking in light, it's engaging in a quantum dance refined over millions of years. Plants have developed a method to utilize nearly all the light they absorb, almost as if they hold a secret that we have yet to discover. If you've ever been curious about how light transforms into chemical energy, the process is truly fascinating. When a photon collides with a chlorophyll molecule, it boosts an electron to a superior energy state, essentially giving it a jolt. This energized electron then travels through the plant, triggering a chain of chemical reactions that culminates in the creation of glucose and oxygen. However, the most extraordinary aspect is that this entire sequence unfolds with breathtaking speed, all thanks to the quantum coherence previously mentioned. Picture a relay race, where every runner passes the baton to the next with flawless timing, losing no momentum. That is precisely how electrons are transferred from one molecule to the next inside a plant. This swiftness and efficiency are absolutely critical, since sunlight is not a constant resource. Plants have adapted to make the most of every sunbeam, even under the most difficult circumstances. Yet, the puzzle doesn't stop there. Quantum photosynthesis is far more than a scientific oddity. It carries profound consequences for how we perceive the world. If we could ever fully grasp how plants accomplish this incredible feat, it could inspire us to develop new technologies that imitate their methods. Imagine solar panels capable of capturing light with the same efficiency as a leaf. Such an innovation would represent a fundamental paradigm shift in our methods of energy generation. Quantum biology is forging new paths in scientific inquiry. As researchers learn more about these phenomena, they are coming to understand that quantum mechanics is not limited to the realm of subatomic particles, but also plays a fundamental part in far more complex biological systems. This realization challenges our conventional models of how life works and encourages us to rethink our entire perception of the natural world. Furthermore, quantum photosynthesis compels us to contemplate the deep interconnectedness of nature. Every single plant, tree, and leaf is an element within a sophisticated web of life where energy continually flows and transforms. Within this intricate system, quantum mechanics serves as a unifying thread, connecting everything from the most minuscule molecules to the vastest ecosystems. In this broader context, it becomes clear why caring for our environment is so crucial. Plants do more than just supply us with oxygen and sustenance. They are also brilliant illustrations of how nature leverages quantum principles to flourish. To protect them is to protect ourselves, ensuring we can continue to draw upon their amazing methods of energy production for generations to come. Ultimately, quantum photosynthesis is not simply an academic subject. It is an open invitation to marvel at the wonders of the universe. It reminds us that even though we may often feel separate from the natural world, we are in fact deeply intertwined with it. Each time we look at a plant, we can be reminded that a phenomenal process, a quantum dance, is occurring, providing sustenance for all of us. In this sense, science is not merely a compilation of data, but a continuous story that binds us to the cosmos and to life itself. Quantum mechanics, with all its mysteries and marvels, is not restricted to the tiny subatomic domain. Its influence reaches into an area that might initially seem entirely unrelated to waves and particles, the evolution of species. Have you ever considered how quantum physics could potentially shape the course of life's development on Earth? As it happens, the link is substantially deeper than we might have first assumed. At its very essence, evolution is a journey of change and adaptation. Across millions of years, species have transformed, mutated, and adjusted to their surroundings. But what if I were to tell you that the fundamental laws of quantum mechanics could be playing a significant role in this grand process? The very notion that minute quantum fluctuations might affect genetic diversity opens up a vast new realm of possibilities. Mutations, those small alterations in DNA that can give rise to new traits, have conventionally been seen as mere accidents or random occurrences. However, some studies propose that particular quantum processes might actually encourage these mutations, suggesting evolution is not just a game of luck, but a delicate interplay between the random and the structured. How could this be possible? The explanation is found in the fundamental nature of particles and their behavior. In the quantum domain, particles are capable of existing in multiple states simultaneously, a concept you can visualize by imagining a flipped coin that, instead of landing on heads or tails, remains suspended in a state of superposition, where it is both at once. While this principle might seem strange, it indicates that nature, at its most basic level, is far more flexible than we typically believe. Consequently, Some theories put forward the idea that this property of superposition could be at play within genetic mutations. It's possible that the very structure of DNA, life's instruction manual, is influenced by these quantum fluctuations. In this context, quantum mechanics transforms from a spectacle for physicists into a vital participant in the drama of life itself. Imagine that each time a cell divides, a tiny quantum spark could be the catalyst for changes in the DNA sequence. This spark might represent the beginning of a new trait, a novel characteristic that grants an organism a competitive advantage in its environment. Beyond this, quantum mechanics could also affect how species interact with their surroundings. Organisms do not evolve in a vacuum. They are in perpetual engagement with other living beings and the world around them, and their decisions and adaptations might be shaped by quantum factors. Under ecological pressure, for instance, minor fluctuations in DNA could trigger a mutation that, while rare, might offer a decisive survival advantage. And what is the source of genetic diversity? Quantum mechanics may be responsible for the sheer richness of variation observed within a population. Rather than depending exclusively on natural selection and the slow accumulation of mutations over generations, we might be witnessing a quantum element that introduces surprise and creativity into the evolutionary process, potentially explaining why some species seem to experience rapid transformations instead of gradual development. But how can such a hypothesis be verified? Research in quantum biology and evolution is still in its early phases, but scientists are starting to explore methods for measuring and observing these principles in nature. The goal is that by understanding how quantum fluctuations can guide evolution, we may be able to unlock some of the most profound mysteries of life itself. A future where we recognize life not just as a series of chemical reactions, but as a phenomenon deeply influenced by the rules of the quantum universe, would have enormous implications. This shift in perspective would not only revolutionize our understanding of biology, but could also provide new insights into health, disease, and how we address the challenges presented by our environment. It is possible that evolution and quantum mechanics are two aspects of the same reality, joined in a cosmic dance that has shaped all life on Earth. As we delve further into this fascinating topic, you may begin to view life from an entirely new angle, one where every small change and every mutation is not merely random, but a manifestation of the universe's most fundamental forces. For many, the question of whether quantum mechanics can play a role in the evolution of species might seem absurd, as if we are fumbling for answers in a labyrinth of pure speculation. However, as we venture into the world of quantum mutations, we start to realize that reality may be far stranger than we imagine. Mutations are the engine of evolution. They are small changes in DNA that can lead to new traits in organisms. But what if these changes are not just the product of errors or environmental adaptations, but are also influenced by quantum phenomena? Think of DNA as a recipe book, where each gene is a recipe, and mutations are alterations to the ingredients. What if some of these alterations occur in unexpected and mysterious ways? A captivating example of how quantum mechanics could influence mutations is the principle of superposition, where subatomic particles can exist in multiple states at the same time. This is comparable to a coin tossed in the air being, in some sense, both heads and tails until it finally lands. In the quantum world, the possibilities are far broader than what classical logic allows. So, how does this idea of superposition translate to the biological world? Some theories suggest that during DNA replication, subatomic particles might influence the nitrogenous bases that form the genetic code. This process could give rise to unexpected mutations that, under the right circumstances, could be beneficial to the organism. It's intriguing to think that the changes leading to new species might not be purely random, but could also be guided by the probabilistic nature of the quantum realm, connecting the behavior of subatomic particles to the biological diversity we see on our planet.
Consider the implications of this. If quantum mutations are real, the process of evolution might be faster and more dynamic than we have previously thought. Imagine a species that, rather than waiting millions of years to adapt to a new environment, could undergo significant changes in just a few generations. This raises a compelling question. Could we be observing a form of quantum evolution in action? One phenomenon supporting this idea is genetic variation. Organisms that reproduce in ways allowing for greater DNA variability, like single-celled life forms, may be more susceptible to these quantum mutations, which could explain why some microbes adapt to environmental changes with incredible speed, such as developing antibiotic resistance in a surprisingly short time.
Imagine if the chemical messages that life forms use for communication were governed by quantum effects. Such a reality could usher in entirely new types of collaboration or rivalry among species, redirecting the path of evolution in ways that are currently beyond our grasp. Researchers are now investigating potential connections between these quantum mutations and epigenetics, a discipline that examines how the environment can alter gene expression without changing the underlying DNA. Should quantum events prove integral to this mechanism, we might be standing at the threshold of a revolutionary change in our understanding of evolutionary science. Of course, this quest for knowledge generates as many questions as it answers, chief among them being how we can even observe these quantum mutations. The fusion of biology and quantum mechanics represents a vibrant and expanding frontier of scientific inquiry. While developing advanced models and simulations offers a promising path to decode these puzzles, we are only just embarking on this exploration. This very possibility compels you to rethink the nature of life, shifting the perception of evolution from a strictly linear progression to a profoundly dynamic process where quantum uncertainty is a key player. Ultimately, quantum-level changes could be central to how all species adapt and survive in a constantly shifting environment. This fascinating intersection of quantum physics and biology provides a fresh lens through which to view life and the cosmos. As science delves into these enigmas, every breakthrough moves us nearer to grasping the intricate systems veiled by the apparent simplicity of our world. Much like quantum mechanics, evolution is an odyssey filled with unexpected turns, where a single finding can transform your entire perspective on your place in the universe. This quantum revolution is not merely an abstract idea limited to physics. It is a gateway to new modes of comprehending life itself. What if I proposed that the enigmas of the quantum realm are the very key to deciphering the secrets of biology? The reach of quantum mechanics extends far deeper than you might think, from the way your own cells work to the process of photosynthesis in plants. Take photosynthesis, for example. The green life that fills your parks and gardens are essentially sophisticated energy converters. Their ability to transform sunlight into nourishment is rooted in quantum-level events, which enable them to harvest solar energy with remarkable efficiency. Within a plant's leaves, molecules behave like miniature dancers, their movements and vibrations tuned to harness nearly every photon of available light. It's almost as if they wield a special power, performing a kind of magic with sunlight. This raises profound questions for scientists. Do the quantum characteristics of these molecules provide this edge? Could it be that they are leveraging quantum mechanics to leap between energy states with a speed that defies classical physics? Picture runners in a race who can instantly teleport from one point to another. That's a glimpse of how quantum effects can manifest in nature.
The scope of quantum biology extends well beyond photosynthesis, with emerging evidence indicating that quantum mechanics may be pivotal to how animal senses operate. Consider your own sense of smell. Studies suggest it might be shaped by quantum events. How else can you explain the brain's capacity to identify thousands of distinct odors with such speed and precision? The explanation could be found in the quantum-level interactions between odor molecules and your olfactory receptors, almost as if every scent has a unique musical signature that your brain can instantly recognize. And the puzzles continue with another captivating illustration: the migration of birds. Have you ever wondered how flocks navigate over thousands of kilometers with such pinpoint accuracy, flying in flawless unison? Some scientific theories propose that they might be using quantum entanglement as a natural compass. You can picture it as an internal, invisible map that gives them an immediate sense of their location on the globe, an instantaneous link between particles that functions like a confidential message encoded just for them. The consequences of quantum biology reach much further than what is immediately apparent. The grand process of evolution, which has sculpted all life on this planet, could itself be guided by quantum mechanics. Is it possible that mutations, the subtle alterations in your DNA, are actually dictated by quantum events? This notion introduces an additional layer of intricacy to the compelling narrative of evolution, suggesting nature is engaged in a game of cosmic hide-and-seek on a scale we are only beginning to comprehend. This quantum revolution prompts you to fundamentally reconsider the definition of life itself. If the principles of quantum physics can shape core biological functions, what does that reveal about our place in the cosmos? The traditional lines separating physics and biology are dissolving, showing us that every facet of existence is connected in previously unimaginable ways. It's conceivable that life, in its most basic form, is an expression of quantum phenomena. Beyond posing new questions, quantum biology also opens up avenues for groundbreaking innovations, particularly in medicine. Picture medical therapies designed to fight diseases at their most elementary level by harnessing quantum effects. The prospect of leveraging quantum mechanics to create novel treatments presents a future filled with promise. While research is advancing daily in this direction, the path isn't without its complexities. Digging deeper into quantum biology inevitably brings us face to face with significant ethical and philosophical dilemmas. How can you define what it means to be human in a universe where the laws of quantum mechanics so deeply shape our lives? The line separating what you understand from what remains a mystery is becoming increasingly indistinct, confronting you with questions about your very existence and your place in the cosmos. The quantum revolution is actively reshaping our conception of life, ushering us into a new age of discovery and exploration, where each finding acts as another piece of a grand puzzle, drawing us nearer to comprehending the enigma of existence. As you venture forward, it is vital to maintain an open mind and be prepared to challenge your most fundamental assumptions. Revelations in quantum biology do more than just fascinate us. They serve as a potent reminder that science is a perpetual journey of learning. It beckons you to be inquisitive, to ask difficult questions, and to never shy away from exploring the unknown. Quantum mechanics is an undeniable part of our reality, and its role in the fabric of life is merely the opening chapter of a story that is only now beginning to unfold. The universe, with all its immense and mysterious intricacies, is like a colossal puzzle that, for all its scale, can be deciphered through its smallest details.
Every breakthrough in quantum mechanics hands you a new fragment of this puzzle, exposing a reality that defies your intuitive grasp of the world. It compels you to reconsider everything you thought you knew about life and the cosmos. But what does this truly signify for you and your perception of everyday existence? Reflecting on these concepts, you might ask yourself, are we alone in this expansive universe? Or is there a more profound interconnection between us and the particles all around us? The idea that tiny particles can be instantaneously entangled, regardless of the distance between them, suggests that you are more deeply connected to everything than you could have ever conceived. Could it be that your actions, thoughts, and emotions influence this quantum network of connections? This sense of awe also extends to our understanding of life itself. Quantum biology introduces the possibility that the foundational processes giving rise to humans and all other organisms are directed by the very same laws that govern the behavior of subatomic particles. Consider for a moment that every breath you take and every thought you formulate might be linked to these invisible quantum principles. Is it not astonishing to think that the essence of your being may be interwoven with the fundamental laws of the universe? As you delve deeper into this line of inquiry, another question surfaces. Could quantum phenomena actively influence your evolution as a species? The answer may be more compelling than you imagine. Mutations, which are the engine of evolution, might not be solely the outcome of random chance and environmental factors. They could also have a quantum component. Is it possible that nature is using quantum mechanics as a tool for innovation and adaptation in ways you do not yet fully comprehend? Consequently, the quantum revolution is not just a sequence of scientific discoveries. It represents a paradigm shift that is rewriting your understanding of what it means to be alive. Each new insight in this domain not only reveals the complexity of matter, but also illuminates the beautiful simplicity of our bond with the universe. What would happen if, instead of viewing yourselves as isolated beings in a vast emptiness, you began to recognize that you are part of a much larger cosmic web? This shift in awareness could open the door to new ways of understanding your relationships and your impact on the world. The implications of quantum mechanics extend well beyond science, urging you to re-examine your philosophy, your spirituality, and your connection with nature. Every decision you make may resonate within the fabric of the cosmos, an idea that can feel both liberating and overwhelming. Are you prepared to accept responsibility for your connection to everything around you? In this quest for meaning, you might also find a source of solace. Quantum mechanics teaches us that while reality may appear bizarre and incomprehensible, an underlying order governs the apparent chaos. This order is not always immediately visible, but it is present in every corner of the universe. Is it not reassuring to think that, despite the uncertainty of life, there is a coherent logic uniting everything you know and experience? As you reflect on your existence, you can find inspiration in the beauty of this interconnectedness. The wonders of the natural world, from the navigation of migrating birds to photosynthesis in plants, demonstrate how quantum mechanics is woven into every facet of life. This should inspire us to celebrate this connection and seek ways to live in greater harmony with the world around us. Quantum mechanics invites you to stay curious and to continue your exploration, as each discovery opens new doors and gives rise to new questions. So, what does the future hold? The answer may very well lie in your own hands, in your willingness to ask questions, to explore, and to learn. Ultimately, looking ahead, quantum mechanics reminds you that you are a part of something far greater than yourself. Each of us, with our unique experiences, thoughts, and emotions, is an actor in the grand theater of the universe. What story will you choose to leave on this cosmic stage? let us contemplate our place in this vast reality, where quantum mechanics not only provides answers, but encourages us to question our own assumptions and beliefs. So, how might we embrace this intricate reality while also uncovering the simplicity it holds? The solution could be as straightforward as opening ourselves up to the boundless potential that envelops us. As you contemplate the cosmos and your own role within it, consider that every minute piece, every single particle, is linked in a web of connections we are just starting to grasp. Quantum mechanics, therefore, is more than a scientific discipline. It's a call to stand in awe of life's complexity and to find the elegance concealed within the mysterious. Through this exploration, we may not only uncover answers, but also forge a more profound bond with the entire universe that surrounds us.